In this video, we're going to change perspectives on integrals and focus on an interpretation of integrals that's more relevant in most scientific and engineering applications than the area inspiration. The idea that the area under a curve can be represented by an integral is absolutely relevant. However, if you look at examples in physics, we don't usually think about area as sort of the building block. Instead, let's recast our integral. So what we had before was the integral of some function, and if we integrated that and we could find a formula for the antiderivative, so that was what we thought of as the antiderivative big F, we would take the function that was given to us, accumulate it from a certain point to another point, and another way to evaluate that integral or find out what that area represented was to get the antiderivative and simply evaluate it at the two endpoints. If we rethink that, though, as being given a rate in the first place, so we're going to erase that, and we'll call this f prime, and we'll call it x still to keep it consistent. If we think of it as the derivative and then the antiderivative again, then another interpretation of this is the net change, end minus start, of whatever the variable is that we're tracking. And the most concrete one of those that most of us can relate to is taking a look at velocity with respect to time. Well, this is an interpretation. If we integrate velocity, it's the same thing as integrating the derivative of, let's call it s for position, because the derivative of position is velocity. And when we integrate that, we get SB minus SA. That's what the fundamental theorem of calculus tells us. When we integrate, we take the antiderivative and then evaluate at the 2 points. Well, that's the net change in position. So when we have a definite integral of the velocity and we integrate, we get the net change in position. That general idea of tracking something of interest, maybe population, but having information about the rate of change. While we integrate the rate of change of population, we're going to get the change in population over a fixed time span. That idea shows up in any number of different guises. If we recast that simply in mathematical terms, the only thing that's changed here from earlier terminology is that this used to be little f of x. The idea being it's something that we were given and then for some reason we wanted to anti-differentiate it. The difference here is just the thought process or the mental model we're using. Here we think of big F as what we are interested in, but for some reason we were given its rate of change. And so integrating that rate of change gives us the value at the end minus the value at the start. And that captures exactly what we mean by a net change over a time interval or over a space interval if it's x is our variable. And so the textbook frames this as the net change theorem, just as an interpretation of that definite integral. For some practice with that, take the scenario where a car is moving at a certain velocity and we integrate that velocity. We're going to get some kind of value back. The question is, what does that represent in terms of the problem environment that we were looking at? Take a moment to think about those four options and then we'll check in. All right. The first thing I think that's most helpful is to remember that this is velocity. When we integrate it, we're going to get position. I'll use s again. And so the fundamental theorem of calculus says we're going to get s of 5 minus s of 1, and that's going to be a net change in position. This is position at the end minus position at the start. So we are definitely looking at the net change in position between t equals 1 and t equals 5. It does not represent a change in velocity. The quantity that we get back is definitely in units of meters only, not meters per second. And so those things don't come out of this calculation. This other interpretation is a little fuzzy. I'm not even sure what it would mean, but it definitely does not give us a position at a certain time. It's the difference in position over a certain time interval. Let's try another. This one's a little more abstract. If h of t represents the height of a child in centimeters as they grow, they're 120 centimeters tall at age 10. Which of the following would represent the amount the child grew between t equals 10 and t equals 18 years? Take a moment to scan down there, think about your answer, and then we'll check in again. All right, so here we're starting at the other end. We want the net change between time 18 and time 10. So we want h of 18 minus h of 10. And that's exactly what we would get if we were to do an integral from 10 to 18 with respect to time. The key thing is to remember it has to be the rate of change in the inside of the integral. So it can't be the original h's, the units don't work out, a whole bunch of things go wrong. But if we had h prime inside, we would have the integral giving us the net change in height, and that of course matches C perfectly. A and B, because of the unit ideas or the fact that we have the amount here and then we're integrating the amount, doesn't lend itself to the scenario we're talking about. It's worth considering what we're doing here though. If we imagine this graph of h of t between 10 and 18, we were told that this child started at 120 centimeters at age 10, and we'd have some other height later on that would grow at different rates along the way. Those slope lines, thinking back to all the connections we had before, those slopes would be what we mean by h prime of t in this formula here. So if we measured daily how much, at what rate they had grown, then we would have that information. This integral here, again, between time 10 and time 18, represents the change in height. This height here happens to be the height at time 10. This value over here, let's sketch this out a little like so, happens to be the height at age 18, and this difference is going to be what we find when we take the integral or we calculate h of 18 minus h of 10. That's the change in h, or the net change. The other answer that was available to us is something interesting. It's just not what the question asked for. When we add plus 120 at the end, that is h of 10. And so we get the change plus h of 10, so over t equals 10 to 18, plus where we started. That's going to give us the actual height at t equals 18. So if we wanted to know how tall is this child when they reach 18 years old, this value here would provide that information. The net change theorem tells us that the integral can only tell us the difference in heights, not the absolute height that we ended up at. So it's an important distinction to be able to make. Integrals, definite integrals, give us how much things change, not final amounts. Let's go back to a little more physics model here. Suppose water is flowing into or out of a tank at a rate given by this, where positive rates indicate flow in. That's going to be relevant. By how much does the water level in the tank change during the first 45 minutes? Well, what we notice right off the bat is that this is a rate of change. It's a rate of volume change. And so if we integrate that, let's do this in blue. So the integral of r of t from, let's call it a and b for now, is equal to the integral of the derivative of the volume. So let v of t equal the volume of water in the tank. So v prime of t dt, these are the same thing. If we look at the units, we have units of volume per minute. So this is actually v prime of t. And so that's going to give us the volume at the end minus the volume at the start time. And of course, that is exactly the water level changing. That is the change in water level. Well, if that's what we want, we now know how to compute it. We're going to integrate the rate we were just given, 200 minus 10t times the units of time. Again, checking our units. This would be liters per minute. This would be in minutes. And so we're going to get liters back out. It makes sense for a change in volume. And we're going to integrate over 45 minutes after t equals 0. So from time 0 to time 45. Now we can actually do the calculations where we do the antiderivative. And we're going to get 200 t's minus 10t squared over 2, evaluated between 45 and 0. And just a quick side calculation, 10 over 2 is 5. Subbing in our values, we're going to have 200 times 45 minus 5 times 45 squared. That's the upper value. And the lower value, thankfully, is simple. It is just that. And if we get to our calculator and type all that through, we get quite a large number for the second term, so the entire sum actually ends up being negative with units of liters. So the tank is going to lose 1,125 liters in those 45 minutes. It's relevant to note that at the beginning, say time 0, the tank volume would actually be increasing, because when time is 0, we would have a rate in of 200 liters per minute. So it's gaining water initially, and then gradually it stops gaining and starts losing water. The net change, the net change, which takes into account both the adding and subtraction of the volumes, ends up being what we've computed here, a loss of 1,125 liters. Of course, there's some fine print in here that the volume initially had to be greater than 1,125 liters. Otherwise, it didn't have that water to lose in the first place. So just keep that in mind when you're looking at the physicality of a scenario as well.